Good morning. Oh, that was great. Hi, I'm Tina Peters. I'm one of the members of the LSST, and I have your morning announcements. This is us from yesterday. The photo will be posted on Slack and on the website later, but here's a preview. Today is Storytime Domain. So during the session immediately following this, and then immediately after lunch in Coronado 1, and you can sign up on the bulletin board outside. The unconference is today in the last session of the afternoon. The deadline to sign up is lunchtime today, so either post your ideas on the board or vote on the board with what you'd like to do during the unconference time. There's a public lecture in this room at 7 p.m. tomorrow. You're all welcome to attend and mingle with the audience. Finally, if you have run a session, then add a summary slide at that URL. If you did not run a session, you don't have to do that. If you did run a session, according to these numbers, probabilities suggest that you have not uploaded your slides. Okay, and now for Fed.
Thank you, Tina. It's me again. Just to introduce the remaining speakers for the science collaborations, we have the 4 more science collaborations. With yesterday, this will make a total of 8 science collaborations. That is all of the science collaborations. So STAR's Milky Way local volume will be discussed by John Gizis, who's one of the co-chairs. Sam Schmidt will talk about the informatics and statistics science collaboration. Rachel Mandelbaum, who's the new spokesperson for the dark energy science collaboration, will talk about DESC. And Phil Marshall will talk on behalf of the Strong Benzene Science Collaboration. You guys take it away.
Should I do this one? Yep. Okay, thank you. I'd like to thank the organizing committee for giving the science collaborations a chance to make these presentations. My name is John Gizis. I'm one of the 3 co-chairs, and I'd like to acknowledge here also our previous chairs who've rotated off in previous years, and also in particular Will Clarkson, who's here at the meeting, and whose slides have been ruthlessly plundered from his LSST at Asia talk earlier this spring. Well, as the name of the collaboration tells you, we are aimed at one of the 4 LSST science pillars, namely mapping the Milky Way. And if you think about what's going on here, there's some Gaia data pictured on the side of the slide. We are living in this dramatic, amazing structure here, right? You know, we used to teach it, you know, there's a disk and a bulge, and, you know, and maybe you might mention the halo, and that's all there was, right? And in fact, this enormous, dynamic, wonderful system that we're sitting in that we can study in detail in a way that we can't with, of course, all of the other galaxies around the universe. And so we're interested in the fundamental properties of stars within 300 parsecs and the accretion history and structure of the Milky Way and the nearby galaxies. Of course, we're in a revolutionary time right now, right? Gaia has been just dramatically changing this field. And so I feel obliged to you that we will point out from time to time why we're interested in continuing to work in this field if we have Gaia, right? And they measured 1 billion stars. So what more is there to do? You should go ahead and read the LSST science book if you find any of this interesting. The only thing I caution you is that the organization of the chapters will seem a little strange because we used to be 2 different science collaborations. Stellar populations and stars, and no one could tell the difference between them, so eventually we merged. And thus we have a very long name, we have 3 co-chairs, and so forth and so on. We still only get 1 vote, though, so maybe it was a mistake. So why is LSST so exciting to us? Well, the main thing is that, of course, you go much, much deeper and fainter than Gaia, than Sloan, Pan-STARRS, whatever your favorite survey is. And that extends not only in terms of photometry, These slides are too small to see all the details, but they're here to indicate to you. It's not just that you go beyond 20th magnitude in terms of photometry, but you also do it in astrometry. So we will measure proper motions. LSST is in effect an extension of Gaia, but for much, much fainter sources. And it can even measure parallaxes. You want the stars to be nearby, as we'll discuss later on, but there's an important science case there. The huge field of view, of course, is important to us, and the very wide color stretch, right? The existence of 6 filters is vitally important to us because you can measure metallicities and temperatures of stars of a wide variety of types. Sometimes the key one to have is adding U. Sometimes the key one to have is adding Y, right? It depends on the temperature of the stars. We're looking at a wide range of characteristics. And of course, there's microlensing applications and all kinds of things. So I thought we'd just show you some data sets that are sort of existing and ongoing surveys. Here's one of the dwarf galaxies, and you can see what Sloan data looks like on the left. You can see how DECCAM really improves the situation, and right, because you've gone to a 4-meter class telescope. And in turn, of course, LSST will be a further advance along this. You'll see how you're going to start probing the bulk of the stellar population, not just the sort of luminous, maintenance sequence turnoff and so forth. There's a lot to be found. This is the latest from Gaia, from one of their press releases and AppJ papers, and you can see that there's all kinds of streams in the southern sky, right? Not just the Sagittarius dwarf that was discovered in the 1990s, but a number of new streams have emerged. They're limited, though, to things that are brighter than 20th magnitude, right? LSST will be probing much more distant volumes, and for these streams, we'll be probing into the main sequence where most of the stars are. The galactic bulge is another exciting structure, right? You can imagine that with multiband photometry, astrometry, proper motions, you can begin testing models of the bulge. And to give you an example of these things, I got this from a DECCAM team, BDBS, Mike Rich and Christian Johnson. And on the left, as you can see, the color magnitude diagram that you get with a 4-meter telescope. Next to it is what you had from pan-stars. And so you can see there's a dramatic improvement in terms of the width of the stellar locus and also the depth that you're going to. And in particular, you can see why certain filters are important. On the left, you see I versus G minus I. But over on the right, they show the data including the U-band. And now the different metallicity populations in this globular cluster have been picked out. Now, of course, if you're interested in your favorite globular cluster, you didn't need to wait for LSST, right? But this is a 200 square degree survey, and this is one of the many clusters they did. LSST will be much more dramatic. And then finally here on the right, I think is a nice case that you can also, of course, map the interstellar dust by doing the multicolor photometry and seeing how the sources are reddened. And so here is a really amazing thing from Avi Saha, who has measured, using a deep DECCAM survey, has measured RR Lyrays. You identify the RR Lyrays, you de-redden them back to their locus, and you get this incredibly detailed structure of the reddening map. So LSST will be able to do this over, of course, the whole sky. Well, I don't think there are enough RR Lyrays at high latitude, right? But that's the idea. And then finally, I did think I should mention brown dwarfs because that's my own field. Gaia has this wonderful HR diagram, which if you haven't ever stared at, it's just, it's unbelievable, the details. But the bottom corner starts to fade out, right? Well, that's just the brightness limit, right? 20% or so of the stars are actually brown dwarfs. And they're missing, right? For the most part, there's a few there. And so LSST will be able to measure parallaxes out to 100 to 300 parsecs for the bulk of the brown dwarf population, L and T dwarfs. And so it really will allow us to define real population samples and investigate the initial mass function. So those are our a few of the many science highlights. Again, I urge you to look at the science book, for example, and of course to look at the new Gaia results. But the structure of the collaboration is that we're organized into 7 working groups by science area. In fact, you might even imagine that once the surveys go, maybe it's really going to be like 7, mini collaborations, because these are each touching different bits of science. The truth is, at the moment, this structure is rather dormant, right? Because this is a science-oriented structure, and with the exception of a couple of the groups here, there's not that much for them to do at the moment, right? So that will come into the concerns and issues near the end. So of course, like all the other collaborations, what have we been doing? Well, our idea is that we want to advise the project on scientific issues. That has certainly been happening. Prepare for LSST science projects. That is where perhaps we have not done quite as much because of the various issues that you've already heard. And of course, conducting preparatory scientific investigations. In fact, there's enormous amounts of work going on with Gaia, with DECCAM, with other instruments that are building up the skills and scientific questions that we need to work with LSST. So what kind of things have we delivered and produced recently? I would say that in the last few years, the main effort overwhelmingly has been the observing strategy, the cadence wars, right? And naively, I thought that because we're mainly concerned with static science, proper motions, photometry, we wouldn't be so concerned about it. But of course, observing strategy also goes into sky coverage. And so you can see that if you look at this map where you can see the wide, fast, deep map, and then you can see these purple areas, which in the old baseline plan were observed, but not as often, you can see that very nicely the Magellanic Clouds and the intergalactic disk and the bulge and perhaps other areas of the galaxy up top, have all been cut out. Right? And so the question is, how often should these things be observed, and what filters, and so forth? Generally, of course, we push for more observations, but various white papers have been produced with different scenarios. And so that will continue to be a major issue for us. And we advocate for observing stars and observing regions, even if they have extinction, because that's where the science is. An example, a really excellent one, that's gotten a lot of thought is the Magellanic Clouds. Newt is over there, I think, and they have produced a lot of thought about what's the right way to map the Magellanic Clouds. Again, the big field of view of LSST is what's exciting. So it's not just a matter that you can do your favorite part right in the middle. We can do that already with telescopes. But you can go way out into the structure of how these two galaxies are interacting with each other and with the Milky Way. So, we're supposed to talk about concerns and issues, right? It's not just a positive rah-rah talk, okay? All right, so this slide is about, the science issues, like what do we worry about with LSST that we want to be good at? We worry about the sky coverage and the cadence. We would like the Magellanic Clouds to be observed, even though they're always at relatively high air mass. The bulge, the plane, there's a lot of science and discovery potential there. Of course, TVS also is concerned with those areas of the sky, but we advocate for them. Astrometry. There's every reason to believe that astrometry should really work. Compared to when I came 5 years ago, the difference is we know Gaia launched, so we have a perfect calibration reference frame, and we know that DECCAM has demonstrated that you really can do wonderful photometry over astrometry too, astrometry over big areas of the sky. So they will exceed the science minimum requirements for sure, but work has to be done to make sure that the astrometry really does work. Parallaxes are a little trickier. You have to be sure that you observe when there is a parallax signal to be found. For the undergrads, you remember you're taking advantage of the Earth's orbit, right? And of course, the time opposite midnight is noon, so LSST won't observe at noon. So you want observations at the beginning and end of the night, right? Twilight. Near zenith, so there's not much refraction. But we just heard yesterday that LSST is concerned about the observations at the beginning and the end of the night. So I'm slightly worried about that, but I haven't talked to anyone at all about it. So we will find out. But the parallax is the only thing that's a little tricky that you want to be sure you do. Point source photometry. The calibration is obviously very important. You want to look for subtle difference in populations. That means, you want the calibration to be really excellent in all the filters. Oftentimes, U, Y, filters like that can matter depending on the population you're doing. So that's a big concern for us. All I do is I walk into a room and they say, oh, you're going to ask me about crowded field photometry again, aren't you, Jesus? Right? So that is my interpretation of my job for the last 5 years. I myself know nothing about crowded field photometry, but the easy way to put it is that there are community standards of what an excellent job would be for observing areas like the bulge and the Magellanic Clouds. DAO, FOD, and similar codes exist. It's very important that either the project produce work of that quality, or somehow someone is funded with an official connection, which is not happening, of course, to do it instead. So that is a very tricky and difficult situation. Star-galaxy separation is another interesting problem. Now, I'm running low on time, so let's just say that these things are, of course, repeats. Everything is volunteer effort levels, right? So there might be 180 people listed on the collaboration, but some of them did a lot of work 5 years ago, but are too busy now. It really varies. There's no funding, that means there's no students, there's no postdocs, right? Data rights and international collaborators are an uncertainty. I don't know what's going on, right? And obviously it's a big concern. We actually feel that there's a lack of effective communication tools. That may be, of course, poor management by me, right? But it's also that, where do we put information and reports that people can access and find again? Community doesn't quite feel like the right thing to people. Email exploders are what us old people are comfortable with, but they're not really effective for other things. So we have a problem in communication. And of course, all these people are not going to, if they don't use Slack already, they don't want to adopt Slack just for checking LSST news. So that's a problem. I'd like to adopt the task force model from TVS that was mentioned yesterday, where we look at specific technical problems, right, without undermining the scientific structure of the working groups. But we're going to discuss that tomorrow. We have scheduled a joint meeting with TVS for those of you probably on the East Coast and stuff, and you can come. And then I also worry somewhat, although again, I just stuck this in at the last moment. I'm worried about organizing follow-up and ancillary observations with other collaborations. There's probably many cases at high latitude where most of the work should be for a kind of galaxy survey, but perhaps some of the stars could be observed as well. And I don't know how to organize that in an effective way. But of course, many other people have been discussing those issues. So that's it for my thing. I've probably used all the time, so that's it. Go to the next one.
We're going to make one small change.
Hi, I'm Sam Schmidt from UC Davis. I'm actually presenting this on behalf of Tom Laredo and Chad Schaefer, the co-chairs of the ISSC, who can't be here today. So for some context, the astronomy and data science communities over the past 2 decades have really realized that there is a real synergy. We have astronomers developing larger and more complex data set in need of new algorithms, and we have the data science community developing new algorithms in need of large data sets. There was a lot of individual work on these types of collaborations. The ISSC, the Informatics and Statistics Science Collaboration, was one of the first to organize this on a sort of larger scale in 2009. We were the first group on the call for new science collaborations beyond the original science collaborations. Since then, other groups have formed. The main idea and takeaway from this slide is that these are groups of scientists, both data scientists and astronomers, trying to advance astronomy through novel data science methods. So who are the ISSC? Again, our co-chairs are Tom Laredo at Cornell, whose main focus is on astronomy, and Chad Schaefer, who does data science at Carnegie Mellon. In addition to our 2 co-chairs, we have what we call the core team, 5 extra people who several years ago got together and had either specific projects in mind, like myself at UC Davis working on PhotoZs, Jogesh and Eric Feigelson at Penn State, Tomasz Budavari at Johns Hopkins, who is joint astronomy and applied math, and Robert Wolpert at Duke. So these are our core members. In addition, we have 72 other members, both astronomers and data scientists, and also 11 affiliate members who aren't official members but who are watching the ISSC for interesting ideas. Specifically, we have a wide range going all the way from pure astronomer to sort of pure data science. Tom sort of broke this up into a few slightly overlapping Venn diagram groups. We have people who are primarily in another science collaboration. I am definitely one of those people. Like Desk, for instance, we have people working on PhotoZs. We also have people using data science and informatics tools to verify our Desk simulations. We have members working on deblending and also large-scale structure. From the transients groups, we have people who participated in the plastic data challenge, and especially there's been a lot of work on identifying irregularly sampled time series data for transient objects. And then I'm listed for galaxies. Unfortunately, this has been sort of dormant for the last several years, using data science methods to identify galaxy SEDs beyond just a simple PhotoZ. Although some of this is in the galaxies roadmap that we put together several years ago. There are also people who are more on the statistics and machine learning side of things who want just access to some data set to try their algorithms. For specific examples, Yanqi Chen at the University of Washington has built a filament identifier and ran it on the SDSS catalog, but there are plans to use this on LSST. Lior Shamir at Michigan Tech has developed an extragalactic object classifier, again applied to SDSS and PanSTARRS data, but will also be applied to LSST. And then Tom Laredo has worked with David Ruppert on using functional data analysis to do light curve fitting for some of the variable sources, as well as SED modeling in the multiband data. Some of these distinctions are a bit artificial. Individuals trained as astronomers, but who have primarily in the last several years worked on data analysis. Eric Feigelson, who if you've been to any of the Penn State summer schools, you probably know, has developed tutorials on time series methods and used them at a TBS workshop. Peter Freeman, who I work with a lot on PhotoZ aspects, has developed LSST-based projects and uses them in data science courses at Carnegie Mellon. And Tom Laredo, one of our co-chairs, has contributed as well to the PhotoZ project and the aforementioned light curve fitting with David Ruppert. And finally, for some reason, Chad gets his own slide. I've known Chad for almost 20 years now, working on astronomy problems all the way back to when I was an undergrad. He has done a lot of the actual organizational work within the ISSC in the last several years, and also additional work just in general for the astronomy and data science community. He also contributes particularly to Desk. Again, I work with Chad on adding empirical emission line models to some of the simulations in Desk in order to predict photometric or spectroscopic incompleteness for our photometric redshift stuff. So Chad is sort of the glue right now, Chad and Tom, holding the ISSC together. So that's sort of a quick summary, not comprehensive. That was based on a census that we sent around last year. But brings us to what is the role of the ISSC? And I think it really is, as Tom put it, going from the statistics-dominated era where we were just adding more galaxies and going root N, to now the systematics-dominated era where that isn't good enough. We're running into new effects that we haven't seen before. These problems require new methods, new algorithms, and different ways of running our analyses. This can be problematic because the gap from going from a new method to actually applying it to the data is complex. It requires adapting your pipelines, it requires new tools, and it requires knowledge of those tools. And so this is where I think the ISSC plays a key role. We have a set of people who have domain knowledge in both astronomy and data science who can hopefully bridge this gap. The key is actually making those connections and getting people with that knowledge engaged in the problems that we have throughout LSST. This leads to one of the biggest problems. This is a pretty broad mandate. I mean, if you think about it, it's really, we want to help everyone with all of their problems that could involve big data. That makes it very hard to have a cohesive focus within a science collaboration, especially with diverse membership. You have people like me who are primarily interested in photos, even galaxies, people interested in transients. So having some sort of focus is a definite challenge for this science collaboration. Building and extending the connections to other science collaborations, I think this is partially a communication issue and visibility, and we'll talk about that in the next slide of potential solutions there. And related is funding. It is difficult to get people to work on things when they're not funded to do it. This is, of course, a problem for all of the science collaborations. But as the next bullet point says, when you have many things to work on, and especially some of the people that aren't primarily astronomy, who are more data science and just looking for problems to work on, it is hard to get their attention and grab them and get them really working on a problem in detail. And finally, there is a steep learning curve in astronomy, just in terms of the language that we use sometimes, but also the details of the problem are very, very specific. So having tools and the people involved who can sort of help ramp up the collaborators who wouldn't be as familiar with the astronomy terminology is an ongoing challenge, but I think something we can address with the expertise of the ISSC. And this interdisciplinary communication is just that, getting the right people talking to each other and make sure they're talking the same language to get a project kicked off. So we've started to think about some solutions for these problems. One of the main ones, again, is just communication and visibility. We recently set up, I think earlier this year, the Ask the ISSC Slack channel. This is a new Slack channel. It hasn't been used very much so far. If you have any quick questions that you think are informatics or data science or statistics, whatever you want to call it, related, please post to the ISSC channel and someone from the ISSC will try and answer your question. But hopefully it'll go beyond just quick questions. Hopefully it will be an introduction to, like, I am working on this class of problem, I have this sort of general question, and hopefully this will be a place where members of the ISSC can help, will start to get engaged and hopefully build real collaborations, either on projects or actually person-to-person collaborations, and have people basically joining other science collaborations. Similarly, we just last month started the slightly awkwardly named Topical Online Presentation Series, a monthly telecon, we're hoping it will be monthly, where we have a subject area related to some deep learning or informatics or data science topic. The initial one was Daniel Muthakrishna talked about real-time automated photometric identification of supernova and other transients. It went very well. If you have a problem in your science collaboration that you think would be interesting to the data science community, please contact Tom or Chad. We can get you signed up. It will open your topic to a wider audience in the informatics collaboration. And of course, everyone is welcome to attend these meetings. I will try and get, it wasn't on the slides, what the monthly schedule will be for this. Maybe we can post that to the Ask the ISSC channel. And then finally, there has been a lot of behind the scenes efforts on the funding question. Again, if we had some dedicated funding, it would be easier to get people working a little more concretely on this. Some of the core members, not myself, have been working on NSF proposals for the ExcelNet and harnessing the data revolution. They've been developing white papers for the decadal survey, and also working on pitches for data science incubator projects to, again, sort of recruit new people and, again, have more concrete projects to really get projects off the ground. So again, I think one of the main issues right now is communication and making connections to other science collaborations. So please take advantage of the Ask the ISSC channel, contact Tom and Chad, and hopefully we can increase the connections between the science collaborations. Thank you.
Okay. Hi, everyone. So a desk is not just an essential piece of office furniture, it's also one of the science collaborations, the Dark Energy Science Collaboration. I'm the fairly new spokesperson of the desk, and I'm going to give you an update on our activities today. Okay, so the desk is the collaboration that's now preparing to do fundamental cosmological physics using data from the LSST. So in the next few slides, by way of introduction, I'm going to talk you through our science goals, what actually are we trying to do, and why is LSST such an exciting data set for doing that? The collaboration, what is the collaboration like, and how do we work together effectively? And what is the collaboration actually doing in practice to try to achieve those science goals? Okay, so we aim to do both precise and accurate cosmological measurements with the LSST. And this single plot is a kind of standard way of communicating why LSST is so powerful. It's also a very busy plot, so I'm going to talk you through some very specific aspects of it. Okay, so we would like to understand the accelerated expansion rate of the universe, and dark energy is what's invoked to explain that. So we'd like to ask, how can cosmological measurements with LSST enable us to better understand the properties of dark energy? And a kind of standard way of parametrizing that knowledge is through the equation of state. How close is it to a cosmological constant? At the present time, that's the horizontal axis, and how much does it vary in time? That's the vertical axis. And those ellipses show essentially our level of knowledge. A large ellipse means our uncertainty is large, so we want small ellipses. And so I wanted to focus you on the larger red ellipse. That's kind of the current state of the art, or where we expect to be in a couple of years, pre-LSST. And then the much smaller black ellipse in the middle is where we expect to be with the full LSST data set using all the different probes of dark energy that DESC plans to use. And so that visual comparison of the much larger red ellipse and the smaller black ellipse shows you kind of an order of magnitude in the area of that ellipse. So we're going to know a lot more about the accelerated expansion rate of the universe due to LSST. An order of magnitude is a real qualitative, not just a quantitative change in our understanding. It's going to allow us to understand the cosmological model much better. Okay, so our early science goals involve optimal use of the early LSST data to minimize the error bars, both the statistical and systematic errors, in a joint probe analysis of dark energy on our way to percent level constraints on dark energy with the full survey. The final thing I want to point out is this plot is a very convenient way to parameterize how much do we know, but cosmology is about a lot more than just a single number, the equation of state of dark energy. It's about understanding, testing theories of modified gravity. It's about understanding the nature of dark matter. It's about constraining massive neutrinos. So there's a lot of interesting cosmological physics that's going to happen beyond the one analysis shown on this plot. Okay, so as a community, we're fairly large. We have hundreds of active members. So as of a few weeks ago, we had 215 full members who have committed a significant fraction of their research time to DESC and have voting rights. We're also an international collaboration. You can see on the pie chart kind of a breakdown of the self-reported, the countries where the full members of DESC reside. And so the largest chunk of the pie is the US. That means 30% of the full members, including many people who are making essential contributions, are outside of the US. So in addition to these full members, we also have so far 12 builders. It's kind of a new thing in the DESC. Those are people who've committed so far at least roughly a year to building up DESC's infrastructure. So in terms of how we work together, we have a publication policy which sort of describes our collaboration ethos of working in the open together, working transparently as a collaboration. We have a code of conduct, and we also have a junior DESC organization for support of early career scientists and their interests. So this is a very busy plot of the working group structure that we're moving towards. I don't want to talk through everything. I just want to point out a few, sort of impressionistic features. So the rectangles are working groups, and you can see there are working groups that are in this blue cross-cutting working group, section on the left, and there are probe working groups on the right. So the probe working groups are essentially synthesizing all of the input you need to carry out one of the primary dark energy probe analyses. The cross-cutting working groups are some element in getting to dark energy science that connects to all or most of the primary probes. So in practice, the way to think about it is there has to be a lot of bidirectional communication. The cross-cutting working groups provide input to the probe working groups, but the probe working groups have to talk quite a bit with the cross-cutting ones about their goals. And so a lot of there's a lot of thinking about how can we get these groups talking and working together effectively. Okay, so to get where we need to be, we need to build software pipelines that are going to let us do this precise and accurate cosmological analysis, so precise, tight control of systematic uncertainties, but also working at LSST scale. So our analysis pipelines are under development. You can see some of these, in our GitHub organization. And the way we're developing them is collaboratively. So these are collaborative efforts, and they're iterative as well. So we have sets of simulations, or we're looking at real precursor data, and we're essentially developing the pipelines against those. So, doing some analysis, identifying issues, and then, continuing to work on those issues. So you can see a plot from one of the early analyses using one of our pipelines. As part of that, when processing simulations and using them to test our analysis pipelines, we're also using the LSST DM science pipelines, and so we're sort of early adopters and stress testers who are trying to provide meaningful and useful feedback to LSST data management. So I wanted to highlight just a few areas of activity within DESK, focusing especially on ones that are of interest more broadly. So the first one I wanted to point out was the plastic challenge, which you heard a little bit about Fed yesterday during the talk about TBS. So plastic was a joint project between DESK and TBS. We have an intercollaboration agreement to support joint projects and papers. So this was essentially a challenge. It was a Kaggle challenge on how well can we classify the light curves of time-varying objects, in light of realistic cadence and noise and so on. And it provided a data set that's actually a useful legacy beyond the challenge. So that work, writing up the results and so on is still ongoing, and we hope this will be a useful resource to the community in the long term. The DESK Blending Task Force has also been sort of informally working with other science collaborations, and for example, in putting together last year's blending workshop at the Project Community Workshop last year, which has a website that remains a great resource with lots of great talks and material. Another activity of interest beyond DESK, of course, is observing strategy. So in response to the call for white papers on observing strategy, DESK wrote 2 white papers, one about the Wide-Fast Deep Survey, one about the deep drilling fields. So as you heard, DESK has a number of different ways of measuring dark energy. Some of them are sort of dependent on the static sky, like measuring weak lensing. Some are dependent on transient phenomena like supernovae. And so we did a fair amount of work, especially Michelle Lochner and Dan Skolnick sort of led a very large task force in reconciling the different competing demands of those different dark energy probes to try to come up with a recommendation that was sort of overall best for DESK science. So in the time since those white papers were submitted, in November, we've been hard at work actually, writing up journal articles on that. So for all the results that appeared in those white papers, there is a lot of, a broader body of work behind that, and so we've been writing that up, and also implementing the metrics into MAF so that the community can reproduce some of the key metrics that we use there. Just to highlight a few of the, basic highlights from the Wide-Fast Deep white paper, the static science probes really depend on having, a large contiguous area and a reasonable level of uniformity across that area at key intervals in the survey. Obviously, the time domain probes are much more sensitive to the cadence, and so there were a few specific recommendations about, gaps in the cadence that would be problematic. For example, for supernovae, avoiding 15-day gaps was important. And all probes, of course, want to maximize the efficiency of the survey. So, for example, removing the 2 snaps in favor of a single exposure. Okay, the final activity that I wanted to highlight in this talk was that we're working on simulating LSST images, and we've scaled up our image simulation infrastructure and our DM stack processing of those simulations in our second data challenge, DC2. Okay, so this plot on the right shows just an image, a snapshot of a galaxy cluster from DC2. These are meant to be, sort of LSST-like images, UGRIZY, 300 square degrees, and we have several LSST years simulated at this point. So there are a lot of analysis projects ongoing within DESK using these simulations. On the bottom left, there's sort of a plot of one, a test of recovery of strong lensing system, images of strong lensing systems. But there are many things happening within DESK using these simulations. However, we also recognize that other groups may be interested in using these simulations, and we've been investigating ways that we can make those data products public so that others benefit from them. As a first taste of that, there's a paper out about the extragalactic catalog that was used as the basis for these simulations. So that paper is already out, along with, that's a release of that catalog to the community. Okay, so more generally, if you're interested in learning about other things going on in DESK, we have a list of all DESK publications, things that are already published and things that were submitted up on our webpage, so I'd encourage you to check that out if you would like to learn more. One other thing I wanted to point out about this is it gets to this question of, DESK as a community. I often get a question of what is it like to work in such a large collaboration, and this snapshot, which happens to show the first 3 publications on the list, gives you a little hint of that. You can see that one of the paper in the middle there has kind of a long author list. That is a group that has been working together collaboratively to develop a code base that underlies a lot of our cosmological theory calculations. And so they've been working together in a coordinated fashion on that. But there are also, within our plans, there are a lot of basic method development and software development things we need to do that are nice opportunities for groups, say, a student or a postdoc, to sort of take ownership of a problem and drive it forward, interacting with the working group, but taking ownership of that work. And so you can see, like, the first project is an example of that. That one has a smaller author list, but still the LSST Dark Energy Science collaboration, because they've benefited from the intellectual input from the rest of the collaboration. So in one slide, I wanted to quickly highlight some things that DESK provides that goes way beyond DESK. The first thing I wanted to point out is that our collaboration policies are publicly available on our webpage. They're under a Creative Commons license, and if there are groups, science collaborations or others who, for example, don't have a code of conduct or some of these other policies, and they'd like an example to work from, we really encourage you to adapt and reuse those as appropriate. There are also a number of pedagogical resources up on our webpage. So we have this very popular event called Dark Energy School at every collaboration meeting. It's a day with lectures on a few specific topics. And I wanted to point out that Dark Energy School is actually not just about dark energy. There have been a lot of lectures that are about the LSST system or statistical methods for astronomical analysis or best practices in coding, things like that are of broader interest. So at this point, there are more than 20 LSST-related lessons up on the webpage, including slides, videos of the lessons, and notebooks. And so that's a really great pedagogical resource that we hope you'll check out. We also produce and release software and data products that benefit the community. You can check out our Xenoto Community. That's where we release some data products, smaller data products. We have Github repositories with released software. And we also have papers describing data sets that we're releasing. For example, the paper about the extragalactic catalog, the simulated extragalactic catalog that I mentioned earlier. If you look at those papers, you can get information about how to access the data set. Finally, as I mentioned earlier, we're also sort of early adopters of the LSST DM science pipelines, and we're trying to provide meaningful constructive feedback to DM via our liaisons, and we hope that that also is of broader benefit to the community. Okay, so like the other science collaborations, I have a slide here about some key issues and concerns. The first one is, observing strategy white papers are in, but the process is not over. And so one of our concerns is how we can continue to provide meaningful input into that process. The second one is, understanding in detail how we're going to interact with the LSST release data products and software tools and the alert brokers. How, in practice, are we going to connect to those and take what we need into our own, analysis pipelines? Another concern is supporting international desk members as they navigate the new data rights model. So you saw on my pie chart earlier that about 30% of desk full members, so we're talking about more than 60 people, are outside of the US and Chile. And many of those people provide essential contributions to desk, so we need to support them as they're working their way through this, the new model. Another thing that I wanted to point out is we're really interested in identifying opportunities for synergistic activities with other science collaborations. I put just 2 examples here. This is not meant to be limiting. I'm sure there are many other interesting examples. So one is sort of a scientific opportunity, studies of the fundamental nature of dark matter. If you went to this session about this yesterday, you heard that there's interest in this in several different science collaborations, and so that's an area where, for many of the things we're interested in doing, we're going to need to collaborate more broadly. Another issue, it relates to these image simulations I mentioned. There's a lot of relevant expertise about astrophysical models, for example, that could improve our image simulations, and we'd be happy to incorporate that expertise to improve our simulated data challenges, with the idea being that it's a gain for us, our simulations are more realistic, but it's also a gain for others who want to work on them. And finally, in the coming years, we're going to be thinking about how do we evolve our mode of work from what it is right now, developing basic methodology and providing input on survey strategy, to what's needed once real data is here and we need to pull together the many strands into a cosmology analysis. Okay, so just to summarize, DESC is preparing to do fundamental cosmological physics using LSST data. We're actively at work developing analysis methodology, doing basic research into methodology, and then developing, validating, and optimizing our analysis pipelines to get them working at scale. And there are many ways that others can engage. So if any of this was of interest to you, you can check out our website or look for all the people with the desk stickers on their name tags and come talk to us. Thank you.
All right, good morning, everybody. My name is Phil Marshall. Most of you know me from my membership of the desk, or also with my role in LSST operations. But as past chair of the Strong Lensing Science Collaboration, Aprigita and Timo have put me on their advisory committee. So here I am to explain what the Strong Lensing Science Collaboration is up to, some of their plans and so on for the future. Let's see. Okay, so strong lensing is, I guess, slightly different in character to most of the other science collaborations in that you can see from its name, it's more focused on a astrophysical technique, strong gravitational lensing, than a science goal like mapping the Milky Way or measuring the expansion history of the universe. So most of what I say will sort of speak to how that fits in with what we're doing and how we're thinking about working with the other science collaborations. So these slides were prepared by Aprigita Verma. She's one of the co-chairs of the collaboration. Timo Anguita from Chile is the other one. Okay, so why is there a strong lensing science collaboration with LSST at all? I think mostly it's because LSST will be transformational for this field of astronomy. We'll be going from relatively small samples of systems that have been studied in great detail over the last couple of decades to very large samples of strong lenses that we can think about using in a different way. And that presents some challenges that I'll try and get to. So rather than single or few object science, we're moving to statistical analysis. We still have the challenge that strong lenses are rare compared to other objects in the sky. And so that means that strong lens detection remains a key program for the collaboration. What do we expect from the LSST survey? Well, something like thousands of lensed AGN, 10,000, maybe 100,000 galaxy scale or galaxy group scale lenses, thousands of lensing clusters of galaxies, hundreds of lens supernovae. Currently we have 2, I think. That's a very interesting opportunity. And around 100 double source plane lenses. I'll come back to that in a second. So there are many science projects that you can do with this sample of systems. And as you'll see, those science projects are of great interest to several of the other collaborations. So the strong lensing working group in the desk is interested in using lenses to do cosmology. Is also interested in using strong lenses to understand galaxy evolution, make sense of transients in the universe, study AGN under a microscope, use them to probe dark matter and so on. So here's a little bit more on those wide-ranging science goals. We're interested in how strong lensing can probe galaxy mass and structure. Interested, as I say, trying to measure the Hubble constant in particular, but dark energy parameters more generally. How to do that with time delay lenses. Also double source plane lenses that give you an interesting alternative probe of the expansion history of the universe. That's work being led in the dark energy science collaboration. You can also probe the dark matter substructure of massive galaxies through the tiny perturbations to the Einstein rings. It's an interesting way to get at the nature of dark matter. And you can also use gravitational lenses as cosmic telescopes, giving you additional magnification on the distant universe. So clearly there's a lot to be done here in connecting to the other science collaborations. The strong lensing collaboration has made a fair bit of progress already on that. There's been a long-standing historical connection with the desk and its strong lensing working group. Basically, that group is interested in using lensed AGN and supernovae for cosmology, but there are lots of other interesting science you can do with samples of those lenses. But we can imagine stronger connections to a number of other collaborations as we go forward. Okay, so here's a schematic of the strong lensing science collaboration roadmap that's being put together at the moment. Here you can see in red, or red and green, are sort of three or four key areas that the group is working on. So discovery of lenses, large-scale modeling of gravitational lenses in order for them to function as astronomical measuring devices, and then the analysis of large samples of lenses. Called out in green is the time delays. This is I suppose the newest thing that LSST brings to the study of samples of lenses. So time delays en masse. So in blue at the top are the follow-up or additional data that is needed to get the most out of the LSST measurements. So additional monitoring, high-resolution imaging from space telescopes and extremely large telescopes, and spectroscopy in support. So that's, again, something that we can coordinate with the other science collaborations. There's also a need for simulations to drive the development of this. It's the same thinking as in the desk. And then down the right, you can see to make accurate models and do accurate analysis, you do need to understand the environments of these lenses, which is something that the LSST catalogs provide in detail. So just a word on how this roadmap relates to other roadmaps. Here's a snapshot from an older version of the desk roadmap, just to highlight that there are areas that the desk recognizes are being worked on outside the desk. And some of those are areas of active development within the Strong Lensing Science Collaboration. So we're in contact with the desk and thinking about how to work together. We have regular telecons jointly between the desk Strong Lensing Working Group and the Strong Lensing Science Collaboration. Okay, so everyone has a big data problem. It's a very personal issue, I know. One of the big data challenges we have with strong lensing is how to find strong lenses efficiently. So they're rare on the sky, which means building pure samples is challenging. They're also complex and varied systems, so it's not so easy to train systems to find them automatically. And so another way of saying that is that no single discovery method is complete, so we're interested in hybrid approaches. So where we are right now is thinking of trying to combine state-of-the-art techniques in machine learning to do automated detection and couple that with large-scale visual inspection through citizen science. And so we have some of the members of the collaboration working actively in both these areas and trying to get to a point where we can really get the most out of the LSST data in this hybrid way. So things that we need to do for that, we need realistic simulations to train these systems on, training both the citizens and the machines. That requires some dedicated development. Lens modeling is a key aspect of this to make sense of the features we see. That's something that needs work as well. And so then there are connections that we need to work on to the data management system and also the EPO group within the facility. So here's another of our big data problems. At the moment when we measure or model strong gravitational lenses in order to extract their properties, it can take a very long time. To do it at great detail with a high-resolution image set can take weeks of analysis time. That's both human time setting it up and then also MCMC exploring a complex and nonlinear parameter space. So we've been actively looking at ways to speed this up. In particular, doing the regression problem with deep learning networks seems to be especially promising. You can see this little headline from the Symmetry magazine getting speed-ups of 10 million or so in the modeling of these systems. So this is something I think that might be of interest to many people around the science collaborations. Okay, the collaboration has given input to the Observing Strategy white paper call. Just to summarize where they got to in that. Basically, the focus is on the wide area survey, just because lenses are rare, and that's where most of the interest will be. There's a need for finding lenses early, especially the arcs and rings, in order to then monitor them for supernovae that go off in those arcs and rings. In order to do well at finding lenses in that mode, there's a need for a high-resolution image stack, the sort of best-seeing image, and also good image quality in the blue band. It seems as though the baseline survey is well capable of delivering that, but there is something to watch for the processing of the images to make the lens search efficient. The DESC Strong Lensing Working Group, with their focus on time delay lenses, gave detailed input on the cadence and the seasons. Turns out for lensed AGN, it looks as though it's a sort of a wash if you improve the time sampling of the light curves at the expense of the number of good seasons or the season length, then it comes out to be not much gain. For the supernovae, it's a similar story to the supernovae as studied in the transient groups, which is to say that the alt schedule type surveys seem to work best, and it's well worth exploring rolling cadence. So there was input given from both the Strong Lensing Science Collaboration and the DESC Working Group on this. Okay, so what are the high priority tasks for the Strong Lensing Science Collaboration? They're in the process of putting together a science roadmap. I think it's nearly done. This is important for laying out the actual tasks that need to be done and support found for in order to get them done before the survey starts. They've just finished ratifying their charter, and I think the next step will be to work on a publication policy to strengthen the collaborations, work together. Clearly, figuring out how to collaborate with the other science collaborations is going to be key for this particular science collaboration. I think the vision is something of a network organization that connects together many of the other science collaborations in order to get the most out of the LSST strong lens sample. There'll be emphasis on providing inputs to the simulations through our connections with DESC, preparations for commissioning and early operations, putting together or collaborating on challenges to drive the development of these discovery and modeling methods, and then connection to the facility in terms of the data management and EPO systems. So just to call out one or two details. The roadmap, I think, is getting to the point where we can define quite well tasks that could be picked up and taken on. So if you're interested in these immensely fun systems, you should get in touch with Aphrodita and Timo. There's a lot of good stuff to be done. One thing I think where the strong lensing science collaboration can play an important role is organizing the follow-up of these systems. High-resolution imaging will be important, so will spectroscopy, and we'll do better if we work together on obtaining good quality follow-up data. So that's something to begin thinking about ready for the survey. So all of these things are limited, same story as with the other science collaborations, limited by both funding and relatedly commitment of people. We think that will change as the data gets closer, but it's something that we need to keep an eye on, and that's why there's been this emphasis on the roadmap, laying out specifically the things that need to be done and could be picked up. Okay, so I'll leave this up for you to look at, but I guess the main message is we're looking at a sea change in the use of strong gravitational lenses for astronomy, going from small samples to big samples, and that brings with it some very interesting problems to solve in terms of finding lenses and then using them in large numbers. So if you're interested, please do get in touch with Aphrodita and Timo. It'll be a fun thing to work on, I think, with LSST. Thanks.
Maybe we can have a couple of questions, if I can call the speakers back on stage, and I will moderate this few minutes of question. Roughly one question per science collaborations. And a reminder that if you want to ask questions, the microphones are on the side, so your best bet is to get up and go to one of the microphones. You don't have to pay to ask a question. It's free for all. Then maybe let me ask a question. So there was a talk about the dark energy working group or science collaboration. So maybe since at least two of the science collaborations that will be mainly involved are here, there was a session yesterday that I did not manage to attend. So do you envision, dark matter, oops, sorry, I'm not sure what I said. But do you envision it being, what do you envision this being among the science collaborations?
So, okay, so that was the session led by Keith Bechtel yesterday. We are establishing a dark matter working group within DESC, with the idea being that there's work on some of the dark energy probes that can also be used for measurements that constrain the nature of dark matter. And so it's very natural to have a group to sort of capture that focus and also the work on connecting to theoretical models within DESC. But at the same time, there are a few different science collaborations, galaxies, stars, Milky Way, and the local volume, and so on, that have that already have people working on some of the measurements that some of the other measurements that can constrain dark matter. So we kind of envisioned that as people start to want to work on those things that cut across science collaborations, we would have an inter-collaboration agreement about working on projects and writing papers on that together. That community already has a set of people working, beyond DESC. They already have an established way of talking to each other. So that's, so that it's not starting within DESC and spreading outwards. It's already broader than DESC, and that's a good foundation for that collaboration.
Thank you. Rachel, thank you for the question.
Okay, that's better. So another question for DESC. I was interested in the image simulations that you're conducting. Have you considered simulating some images from the galactic plane, which would be also of interest to many other science collaborations? Or can we work with you on that?
What I would say is, come talk to us. we should have a discussion about this and what that effort would look like, what would be involved to get that going, and, what science would it enable. But, we're interested in having those discussions, so.
Okay, sounds good, thanks.
As a matter of fact, somebody was asking me yesterday if you include solar system objects in your simulations. So obviously there is a lot of interest in the simulations that has begun doing. I don't see any other questions. Yes? I'll repeat the question. I'll repeat the question, which is, what about the rolling cadence, which has shown to be good for supernovae, but not so good for lens supernovae? Can you comment on that, Phil?
So I think this is a clarifying question. So I was talking about two things on the same slide. I think where the rolling cadence is maybe not so relevant is for the lensed AGN, where you have the long stochastic light curves and you need both long seasons and high frequency sampling. For the lens supernovae, as far as I understand it, they have very similar needs as all the other supernovae. And again, rolling cadence looks like it is promising there.
Okay, I think I really don't see any more questions, so we can move on to lightning stories.
Okay, everyone, I am pleased to present this year's round of lightning stories. This has proved, according to our surveys, to be one of the most popular sessions at the last two project and community workshops. So today we have 4 speakers, and we'll also have 4 speakers tomorrow. I just want to state my appreciation for these folks being willing to put themselves up here. We often speak about our science and our technology and things that are much separated from our personal lives. And so these brave folks are up here to tell you a little bit about themselves and how they came to work for LSST and what they do for LSST. So the whole idea of this is to just kind of get us some idea about the people who are behind this work. And Ian has decided that Giovanni will use a lapel mic. And I have been instructed to kind of sing his name during the introduction. So without further ado, may I introduce to you Giovanni Corvetto.
Hi, good morning. Okay, again. Hi, good morning. How are you? No, it's okay. How are you? Great. Yeah, that's okay. My name is Giovanni Corvetto. So I am from Chile, and this beautiful baby is me. In 1975, I was born in the beautiful city of Coquimbo. Coquimbo is a port of Chile. And perhaps some of you know Coquimbo because it's the port through which is all the part of the telescope arrived. Actually, in September, the TMA parts will be in Coquimbo. So it's a very important port for LSST, and it's my hometown. It's in Chile. Coquimbo is in South America, Chile, right? And when I was very, very young, I lived my beloved Coquimbo city for a very far, far away island in the North Atlantic. Some of you recognize this picture? What is it? Anyone? Iceland, perfect. I was working in Iceland for 7 years. And Iceland is a unique country. Actually, they have its own language, the Icelandic. And Icelandic is spoken by 370,001 people, which is 370,000 Icelandics and 1 Chilean, me. But I returned to Chile after 7 years, but I think I was missing the snow and cold, and I moved myself again to Canada, the beautiful province of Quebec. So I worked there for 2 years for a transportation company named Mega. But after 7 years in the cold, working for the geothermal drilling company, and 2 years in Canada, I think I was kind of tired of the snow and cold and returned to my country. So I was looking for something very hot and warm, and guess what? Chile have the Atacama. So I moved to Chile again and worked for several years in the copper mining industry in the north of Chile. So quite a bit, right? North, south, snow, desert. Anyway, I am a proud father of Renata Emilia, 12 years old, a very smart girl, and the sun shines. And currently, I spend the days of my life with the love of my heart, Andrea Gabriela, my partner and my love. After working in the Atacama Desert, the mining industry, I was reading the newspaper. Yeah, peace to you. 2 minutes. Oh, sorry. I didn't know it. Okay. So I am a coin collector. So if somebody have a quarters, we can trade. And also, I am a true fan of the Coquimbo soccer team. Go Pirates! Yeah. Well, at LSST, I was the responsible for the safety of the base facility construction, the new base facility and the data center. We worked together for 2.5 years with the contractors Rencoret and GAG, keeping the people safe. Everybody's safe. Right now, today, I am the LSST safety supervisor at the summit site. And together with Sandra and Sergio, we are trying and make all the effort so the people stay safe and sound. The most satisfactory part of my work in LSST is to know that at the end of the day, the effort and the knowledge of Sergio, Sandra, and me are contributing for the people stay safe. Not only at the workplace, because our contribution is beyond the workplace. Because every time when a worker returns safe home, it's a family waiting. It's a family who can continue with the dreams, with the goals, and a better life. So somehow, Sandra, Sergio, and myself are make a contribution for make the people more happy. Thank you. Last one, sorry. Last one, yeah. I want to invite everyone for tomorrow 11 at Agave for the safety presentation breakout. And also, I want to ask you if I can take a selfie. So, hey! Thank you.
Okay, excellent. Now, for our next speaker, she is going to share a couple videos which are absolutely worth your attention, but they also require the internet. So if you don't mind maybe switching your Wi-Fi connection off for a couple minutes to definitely watch some videos that are worth it, then I will bring up our next speaker. Thank you very much. Yusra Al-Sayed.
Thank you. Good morning, everyone. I'm Yusra Al-Sayed. I work on science pipelines for data management at Princeton University. I really love these lightning talks because you learn all these fun facts about your colleagues, like they have mad crochet skills. I can't crochet, but I have been dancing for as long as I can remember. Literally, my first memory was when I was 4 years old, dancing in my living room along to a ballet on PBS. I fell, cracked my head on a chair, blood everywhere. Mom had to take me to get stitches, freaking out. But that didn't stop me. She enrolled me in ballet class, and I'm still dancing today. Most recently in a Princeton grad student's Dance Your PhD all astronomer production about supernova. More information, more about this later. How did I get here? I majored in physics and computer science, and when I graduated, I ended up in a management consulting job. I built databases for corporate bankruptcies and e-discovery for fraud investigations. But most of the time, I'm the one who felt like the fraud, especially when people were asking me when I was going to apply to business school or law school, because it was really the technical aspect that interested me. I was looking for the next data management challenge, and I, no joke, in 2008, read about LSST in Wired magazine. It informed me that LSST was going to produce petabytes of data, a movie of the sky, and have first light in 2014. So I enrolled in an astronomy PhD program at UW. The DM folks there, Simon, Russell, Andy, welcomed me, and the rest is history. So I've been at Princeton now for 3 years, and I wear a lot of hats. I'm 40% data release production developer. Data release production is the part of the software pipelines that supports static sky science and statistical studies of variability. We think a lot about how to best combine the multi-epoch imaging to squeeze the most amount of information from the data. There's one part, the part that I work on the most is co-addition, which we normalize and stack the images to essentially fake a longer exposure time. I also have a 40% administrative role managing for the talented and ever capable DRP folks. I work to maintain a sense of autonomy, mastery, and purpose within the group. Maintaining our sense of mastery can be especially challenging when we have a true master, very experienced individual in the group in the office next door. I'm also 20% scientist. I build statistical studies of variability selected objects. LSST will be able to observe over 1 million quasars between a redshift of 4 and 7.5. But we won't be able to get spectroscopic follow-up for all of them, or confirmation of all of them, all the candidates, if we're not very efficient and use variability information. We know that LSST will excel at this, but what really excites me is what we don't know LSST will be able to do. Because with every new technology comes a lot of unexpected surprises. Because LSST will allow us to find the rare variability events, the rare transients that we haven't seen before, that we can see by always watching. Much like the technology of everybody having a cell phone video camera in their pocket has given us videos like these when we've always been watching. And I don't know about you, but I can't imagine, do you really want to live in a world without videos like these? Finally, what is going on here? A picture is worth 1,000 words, but it doesn't do much for dance. It's not until you play the whole video that you see that we are the envelope of a star undergoing a supernova and are about to explode. And I envision, so much like we can't imagine watching dance or recording dance and appreciating dance without video, I see a future where time domain astronomy becomes so prevalent in the LSST era that in many subfields we can't imagine doing astronomy without the temporal information. Because for the first time, we'll be able to watch the cosmic dance in its entirety. Thank you.
Okay, that was great. I am not going to dance on stage. And next up, we have someone who I have the honor of working with every day. This is a member of the EPO team. Oh, yeah, sorry, Lauren Corliss. You know who I am.
Hi, everyone. So as Amanda mentioned, my name is Lauren Corliss, and I'm the Deputy Director of Education and Public Outreach here at LSST. I've actually only been with the project for less than a year now, so this is my first project and community workshop. And to be honest with all of you, I didn't necessarily imagine myself working for a telescope. I am an astronomer by training, so I did my PhD at Columbia and did 2 years of a postdoc at Johns Hopkins before accepting this position. But I've spent my whole academic career running and analyzing cosmological simulations to understand how galaxies form and evolve. And in particular, my research is focused on how gas flows into and out of galaxies and predicting the observational signatures of those processes. And so this is an image that is near and dear to my heart. It's one of the galaxies that I've looked at for literal years now. And it's like super exciting. This is an H1 distribution of the gas around a Milky Way-like galaxy at redshift 1. And we have all this great filamentary structure, this dwarf galaxy flowing in. But all of that begs the question of how did I wind up working for LSST EPO then? So for me, doing a dissertation was a really fabulous experience. I learned a lot. I grew as a person and as a researcher. But I think we all know it has those moments where it's just incredibly frustrating. You have weeks where none of your code is working, none of the plots look the way that you're expecting. And so while I was going through that process, I was trying to find a way to remind myself why I was even doing it to begin with. And for me, the way that I did that was by doing outreach. And so the goal of outreach is really to communicate to people that science is cool, that astronomy is the best part of science, and that hopefully they learn something along the way. And in going through all of that is how I refound my love for astronomy every time I went to a new opportunity or a new place to go and do outreach. So this is just some pictures showing some of the things I dove headfirst into. I was getting my PhD in New York City, so there were an endless number of ways to do outreach with any audience that you can imagine. So whether it was taking telescopes into classrooms, going to science centers, giving public lectures, all of that was how I was able to, like I said, refine my love of astronomy. And then when I found out that that could be my job, my full-time job could be thinking about outreach, yes, that is the job that I want. And so I'm really happy to be here and to be a part of this team. But I think when we all think about outreach, we do think of the kinds of activities that are on these slides. We're going out, talking to people, which is a huge, important part. But we are in a construction phase, and we're part of the project, so we're also focusing on how we can build EPO materials that will help further that communication and facilitate that communication in the future. And as a team, we're focusing on using web technologies to do that. And so when I was trying to think of what is my typical day as part of the EPO team, I'm constantly wearing different hats and doing different things. And so in a single day, I could be thinking about formal education content, developing data visualizations, thinking about long-term strategies. But at the end of all of that, my single most important responsibility for the team is defining and assembling precursor data. We want to be able to really build the things that we're designing and to test them with people to make sure that our message is getting across. Some of the science collaborations have mentioned doing work like this too. It's not a unique problem. But I think one of the things that's particularly challenging is encompassed by this slide, which is that by design, EPO is trying to highlight all of the science that is being done by the telescope. And so in a single year, I've had to delve into all of these communities, only one of which I had been a part of before taking this position. And so I think this does a really good job of representing for me my favorite part about this job, but also the most challenging part, which is that I get to learn all of these great things about these fields and all the work that everyone here is doing. But I also need to assemble all of this data for all of these different fields, which can have different nomenclature, different databases, different ways to access those databases. And at the moment, I'm doing most of it by myself. So it's a lot of fun, but it's also pretty hard work. But I want to take a moment to also encourage you all that get involved in EPO. We're probably focusing on your science in some way. I'm running a session later today called Bringing the Alert Stream to the Public, where the goal of that particular session is to think about what are these new discoveries that the telescope is going to be making, how can we take the huge potential for that discovery, and make sure that we're really capitalizing on it in the things that we're planning for the website. But if your schedule conflicts or you just have had a passing thought of EPO sounds interesting, come and talk to me because there's a way for you to get involved, no matter how small, really. Because at the end of the day, what we're really trying to do is highlight all of the work that you all are doing, and I'm really looking forward to when we get to the point to launch all our materials and share LSST science with the world. Thank you.
All right, and so our last speaker of the day, I want to especially thank because not only is she behind this entire event and a part of all of those organizing committees that exist, she stepped in at the last minute to give this presentation after somebody had to cancel. So I'm very impressed with that, and thank you so much to Ranpal Gill.
Good morning. I know I'm standing between you and the coffee break. Sorry about that. As Amanda said, I'm Ranpal Gill, and I'm part of the communications office and a senior manager in the project office. Most of you probably do know me. Yes, I am the very same person that has been bombarding you with emails about the Project Community Workshop for the last few months. Sorry about that. Fun fact, which is not really a fun fact, is I really don't like feeling cold. The really fun fact is I did, however, spend 9 days chasing the aurora around Iceland, and that's a picture of me looking particularly cold. All right, other stuff about me. That's me, age 7, holding my nephew. I've been an aunt since I was 7. I have 9 nephews and nieces. I'm one of 6 children. I have 4 older sisters, 1 younger brother. I guess my parents wanted a son. And the last picture on the end with the James Bond looking guy, that's me a few years ago when I was much younger on my wedding day. Slightly less interesting stuff. I have a computer science degree and an MBA, which I got in the UK. Previously to joining LSST, I worked at IBM, Honda, Lloyds Bank, and the European Space Agency. I was born in London in the UK, but I left over 20 years ago. And since then, I've lived in Germany, the Netherlands, Gibraltar, Spain. Now I find myself in the USA, and I have no idea where I'll be next. I speak a few languages. Punjabi is my mother tongue. That's from the northern part of India. Obviously also English, and a few people have told me that my Spanish isn't too bad. Along the way, I have tried to learn German, Dutch, and Mandarin, and maybe can slightly get by. So what do I actually do for LSST? Half of my time is spent working for the project office as senior manager, where I am the chair of the Change Control Board. I also help out with documents that go into our various reviews, come up with information that might be useful to project members, ones that might be traveling to Chile, for example. I also maintain the builders list. Builders list is a list that contains lots of names of people who have spent at least 2 full-time equivalent years on LSST. Also, this event, which Amanda also mentioned, coordinating and getting the programming together for this event does take a lot of that, 50% of my time. But I'm also heading up the communications office and spend a lot of my time managing the communications team. And that can involve things like the digest, which many of you are probably signed up to, and also putting out news items on our website, setting up booths and town halls for the various conferences that we go to, photography and videography of fun things that have happened, like ships arriving in Coquimbo. We do a lot of the social media, so if you see anything on your social media channels, that's come from the communications office. Right now, the summit facility is shaping up and becoming so real that we have actually started working on designing what some of the signage up there might look like. And also frequently we send out the Communications and Culture Survey, which many project members should have received, and the deadline for that is 30th of August, just a plug for a reminder. I'll leave you with information on how to get in touch with the communications team or just to keep track of what we're doing every day, and a pose by the communications team posing as LSST. Thank you.
All right, that's it. Thank you so much for your attention. You'll hear from 4 more project members tomorrow, and enjoy your tea.